So this is in continuation with our early discussions on clustering, data clustering, and today we are going to look at a neural network-based approach for clustering. This is called self-organizing maps, or SOM. To be very precise, it's called SOM. That's the name of the person who came up with this algorithm, this particular method for clustering. It's essentially an unsupervised network. So far, all the networks that we have seen, the neural network that we have seen, are supervised networks. This is an unsupervised network, and this is related to clustering. Primarily, this is used for clustering, and what it essentially does is it creates a two-dimensional map of your data points. That's what it is. And let's look at that algorithm, and then we'll come back to the slide probably later. So this is the general architecture of a Kohanen self-organizing map. This is the basic form. So this has a two-dimensional map of neurons. You can see that. And there is an input layer. So there is a two-dimensional layer of neurons. You can see that. You can see a two-dimensional grid of neurons with lateral connections, lateral meaning sideways connections, 2D grid. It's called a Kohanen layer, right? And these are the input nodes. Primarily, like this is where you apply your input. So this will, the number of nodes here will depend on the number of dimensions of your data set. Primarily, like if your data set is described in terms of 50 dimensions, there will be 50 input nodes. And this will depend on the kind of abstraction that you're looking for. How many will decide how many clusters you typically look for. So in this case, you're looking for the context and abstraction with 9 clusters. So this is a two-dimensional grid of neurons. This is an input layer where the input, every neuron in the input layer will be connected to every other neuron in the two-dimensional grid, the Kohanen layer. You can see that. So it's connected here, it's connected here. Likewise, it's connected to every other neuron in the 2D grid. Right? This is what it is. This is called. This is a basic architecture of a Kohanen self-organizing map. And let's see how does it work. So this is your new input vector. Your input is presented to the pass through the input neurons. Let's call the input vector, let's label the input vector as E, having n dimensions, E1 to En. This is your input vector with n elements. All right. And for each of the neurons in this layer, all right. So if there are how many neurons, how many connections will be here? If there are, what do you call, this particular neuron will be connected to 9 neurons in the 2D grid, which means that if there are n neurons here, all right, n neurons here, which is equivalent to your dimensionality, all these n neurons will have 9 connections, all right. So U is essentially the weight vector between the input and the Kohanen neuron layer. So you will be like, it's essentially the weight vector, primarily like the weight vector between the every neuron and the input layer. So for example, let us consider this particular neuron. All right, how many connections will this neuron have? The neurons will have, see, connecting here. Likewise, this neuron have n connections. So the dimensionality of the weight vector corresponding to this neuron will also be n. Right? For the neuron I, the weight vector corresponding to neuron I, we call it ui, will have n components. Right? And how does this algorithm proceed? The vector is passed through the input neurons. So E vector is passed on, and every neuron in the Kohanen layer will have a weight vector with n components, which is U vector. Each Kohanen layer neuron will produce a value which is nothing but the Euclidean distance between the presented input and its weight vector. All right. So you get the Euclidean distance between the presented input and each of these neurons in the coherent layer. So then what happens is, that's the interesting part. The coherent layer unit with the lowest Euclidean distance, what does it say? That will be the unit which is closest to the original input vector. We call that, we label that as the winning neuron. We call that the winning neuron. So the output, right, of this particular 2D layer will be, it'll fire only one neuron with the lowest value for this Euclidean distance. So input is presented, each of these neuron can compute primarily, like the computation happens there is, you compute the Euclidean distance between the presented input and the weight vector corresponding this particular neuron. Likewise, you got Euclidean distance for each of these neurons. So among these neurons, one of the neurons will have the lowest Euclidean distance, and that neuron will be called the winning neuron, and that neuron will be fired. So what essentially happens is, the input get presented to the 2D layer. In the 2D layer, each of the neuron will compute notion of distance. The one with the lowest Euclidean distance measure used is Euclidean, and the lowest Euclidean, the one at the lowest Euclidean distance will be labeled as the winner. And the strategy is also called winner take all strategy. The winning neuron is considered as the output of the network. And once that is done, what is happening is, you basically, like, you try to update the base of the winning neuron and its neighborhood. That's the primary operation over here. So let's assume that this is the winning neuron for a particular input present to the network. So the winning neuron and somebody in its neighborhood will get its weight updated. Let's look at the formal weight update formula. The weights of the winning neuron and its neighbors are updated so that they move closer to the input vector. So essentially, like, the weight update formula would be, EI is a input, EJ is the input, and the UIJ will be the corresponding, basically the weight vector corresponding to the ith neuron, and so UIJ will be the dimension of what do you call that, the jth dimension of that input. What you do is, the delta UIJ, primarily, like, the change in weight would be a learning rate alpha into the difference between the presented input and the weight vector, right? So essentially, like a scaled down version of the difference would be taken as the weight, is the increment of the weight, primarily the change in weight. And what you do is, you update the weight. So basically, the new weight would be delta U will be added to UIJ, the old weight, and you keep continuing. And the interesting part is, you don't just update. So when you present an input to the 2D layer, and when one of the neurons becomes a winning neuron, you don't just update the weight of just the winning neuron, you'll also update the weights near to it, weights of the neurons near to it. It's called the neighborhood. How do you decide the neighborhood is an interesting aspect. So you can read here, the winning neuron and its neighborhood are updated, right? What you do is, you typically start with a large neighborhood. At times, initial approaches where you can even take what you call, say for example, if you have a 2D grid, you can see, like, you can look at, say for example, if this is my winning neuron, I can update the weights of everybody at a one hop, right? This is, in this case, is not very evident. Think of a context where there are 100 by 100, there's a 100 by 100 map, and I can update the weights of what you call, say these 4, or I can update the weights of this 8, or I can, this is one hop away. It's basically from the winning neuron, it's one hop, meaning an edge away, right? I can take 2 edges away, I can take 5 edges away. So that is the definition of a neighborhood. So what you essentially do in these kind of algorithms is, neighborhood size is typically taken to be a very large value initially, right? I mean, at times, right, people even take half of the layer, the entire half of the, what do you call, the network, the 2D layer would be taken as a neighborhood, and neighborhood size is reduced in a linear fashion, meaning like if you have, what do you call, if you have a very large neighborhood, you keep reducing the neighborhood as you go along, right? As you present more and more points, you keep reducing the neighborhood. That's one of the strategy. And in the neighborhood, what you do is, in the neighborhood also, you update the weight. How do you update the weight? You update the weight based on this particular equation. Primarily, like the update in weight is corresponding to what do you call, the change in the difference in the weights of the winning neuron and the presented input, and multiplied by a learning rate which is between 0 and 1. So you update the weight. So this is also called winner take all networks, Kohanen SOM. And the learning rate, how do you, and the natural question that you may have is, how do you decide the learning rate? Learning rate also is typically you start with a relatively high value and then decreased in a fashion as shown here. So where, I mean, this is not the only, you can even, there are cases where you have a, you have another multiplication factor. Primarily, you can even reduce it in a linear fashion, or even there are cases where you reduce your learning rate in an exponential fashion. Depends on the kind of what do you call, the flair of algorithm that you want. Here, alpha t at any moment, alpha t will be alpha 0 is the initial thing, 1 minus t by t. T is the current training iteration, and t is the total number of iterations. So basically, like you keep reducing the learning rate, you keep reducing the neighborhood, and the algorithm proceeds like this. You begin with a random initialization of the weights between the input and the Kohanen layer. Each training vector is presented to the network. The winner neuron is found. Yeah, basically, like what you do is, the winner's neighborhood is identified, and you keep what you call, updating the weights of the neurons in the neighborhood. So that's what it is. That's how the Kohanen self-organizing map works. Essentially, if you look at it, this algorithm finds a 2D map of your entire data set. That's what it is. And the 2D map will have a will respect the spatial aspect of the context. So that's where I wanted you to come back to the slide. So these are unsupervised networks closely related to clustering. They don't require target output. So this is, you don't have to have labeled data here. Inputs are connected to a two-dimensional grid of neurons. Neighborhood relations are explicitly maintained, meaning each neuron can have lateral connections with neighbors. So, and also the neighborhood is updated. It's a topology preserving mapping. So it's actually like kind of topology in the sense of the structure of the spatial structure will be preserved. And so it preserves what do you call, the topological structure which is implied in the data set, primarily because you start with the initial thing, and then you keep updating weights based on that physical nearness. And then beyond a point, you can see that the nodes which are nearby will capture a representation. The weights correspond to the nodes which are nearby will correspond to closer clusters compared to the ones which are far apart. So it's a structure preserving map, and it essentially gives you a two-dimensional map of the entire data introduced by Kohanen. And this is the basic flavor, the basic recipe. There is enough of work around it, where people have come out with modifications on how do you decide on the neighborhood, like how do you update the learning rate, and even mechanisms where what sort of neuronal what do you call, units will make more sense, and how do you theoretically what do you call, analyze the performance of such topology preserving maps. So there is enough of research out there, and if some of you are interested, this is an interesting kind of algorithm. and I want you to have an understanding, primarily like a feel of this particular type of neural network, which is an unsupervised neuronal architecture, which is originally designed for clustering. Right, that's all on Cohen and SOM. I'll just stop the recording.